Hello? Hey. Perfect. Hello, everybody. Welcome back. I'm pleased to introduce our next speaker for the deep dive, Mourjo Sen. He is a senior software engineer from Booking.com, and he is going to talk about resilience in microservices with congestion control. Welcome.
Thank you. All right. Hello, everyone. Welcome. Thank you for coming on a Tuesday morning. So thanks a lot for coming, and thank you for introducing me. It's really an honor to be here. Before we get started, it's a heavy-handed title. How many of you are aware of what microservices are, or have at least worked with them? That's quite a lot. So that'll make my life easy. If you have any questions, just shoot them out. But today, my topic is about resilience. We are all talking about resilience the whole day. My topic is about resilience in microservices, especially with congestion control. But before getting into the meat of it, I'd like to say namaste. So I'm originally from India, and that's how you say hello. In Dutch, I think they say good morgen. Am I getting that right? Yeah? All right. So namaste, that's how you say hello in India. I was born and brought up in India. I was there working as a software engineer for 8 years before coming to the Netherlands for the last 2. And I've been working at Booking.com since 2023. And me and my wife have been here in Amsterdam since then. And over the course of my career of about 10 years, for the last 5, I've been focusing on both learning some topics and talking about it and writing about it in public, because some topics I feel that there are very, very far-reaching consequences. Simple on the surface, but have far-reaching consequences. And that's what brings me to this stage today as well, because I want to start today with discussing what we measure when we build systems, because we build systems for our customers, and we would like to measure what matters. And what matters really is what matters to our customers, and that's customer experience. So we would never want to give a bad customer experience. So for example, if you open a website and it's always crashing, or you're getting timeouts, or you're just getting a bad experience, you don't want that. So to prevent this from happening, or at least to know that this is happening, what we do is we try to measure what happens so that we detect something is going wrong and then we handle it, right? But unfortunately, the way we do it is that we measure some metrics, very local, and somehow that misses the big picture. So what I mean by that is, in a typical microservices system, what you might find is there are, so you might have a team that owns the backend of an e-commerce website, for example, and internally you might have some kind of a gateway or a service mesh, and you might have some other team that owns a different part of the ecosystem or the customer domain. So let's say the customer wants to see all the products on your e-commerce website. The backend knows that it has to call someone else that is responsible for maintaining the inventory. So it goes to the inventory service, and the inventory service is a microservice on its own right, maintained by a different team. And that service has its own database, and that database is queried. And the query results come out of the database, and then the inventory service responds via the service mesh, goes to the mobile backend, and that's how the customer sees all the products, right? So your e-commerce website, customer comes, lists all the products. All of these things happen in the background, and then the customer sees it. Now, suppose someday there is a latency increase. You get a mobile pager alert or whatever, and the team wakes up in the middle of the night, investigates. So first thing we do is we go to something like Grafana or some dashboarding tool, and we see that indeed there is a client latency increasing, and it's increasing quite sharply here, because here what it shows is that each request is taking up to 2 minutes. And that's not something we want. If I open some website and it takes 2 minutes to load, I'm not going to use it, right? So that's really bad. So we don't want this. So this team knows that the request goes to another team, so they wake them up. But the inventory service is starting to see that it's OK. There is a bit of increase. There is some more extra requests, but it's all 200. It seems to be all healthy. What's even more confusing is that the inventory service sees that there is a flat response time. The service is working well. It is returning 200s. It is returning responses at the rate using the same amount of time as it was before the alert went out. So what's going wrong here? There is a clear disconnect here between what the client observes and what the server measures. And that is where the metrics are very localized into the inventory service. So there's something going wrong here, right? The client is what we care about, but the downstream microservice seems to say that everything is fine. And this can happen because, let's say that inventory service is built as a Spring Boot application. It doesn't need to be a Spring Boot application, but let's say there's a method there that does the computation for the request. And it's very typical to say that there is some kind of a timer or some kind of an annotation to measure how long this method takes. And therein lies the problem. What we are measuring is very local to this service. It is only measuring the execution time of this particular method. But clearly, that is not the whole story, right? Because what the client is observing is an end-to-end observation, because that is what matters to the customer. We are building a service because we want to provide a good customer experience. But what we are measuring is very local, and it is clearly disconnected. And that is probably because this metric is measuring only a tiny part of the request lifecycle. And that is not good enough. That misses the big picture. So how do we get out of this? First of all, we recognize that there is a problem with the localized view, so we need to do better. We need to focus on the flow of requests. Now, requests is what the customer really cares about. That's why they come to our service, right? So the customer came to us, made a request because they wanted something from us. That is the unit of business value to us. So we need to track that. But what really matters is not just the request to one microservice, but the end-to-end flow. Because until the request goes back to the customer, it's useless. It doesn't matter if one microservice is doing fabulously well, if the caller is extremely slow. It doesn't matter. That's work wasted. So we need to look at the end-to-end value stream, both for the business as well as the request lifecycle. So how do we do that? All right. So how do we measure the flow of requests through our microservices? Let's take a very simple example. This is typically the simplest form of a microservice. You have some users making some requests to a server. Server makes some queries to a database. The database dutifully responds with query results, and then the server responds to the client. That's all good. That's normal. That's what we expect almost 99% of the time. But let's assume now that there are more requests coming in. Say there is a Black Friday sale or something on your e-commerce website, and there are more users in your system than you expected. And when this happens, each request has to find its way through let's say, a crowded street, for example, and then it finally reaches the server. This is where our local measurement started, right? The annotation that I showed before. But by this time, it's already a bit late, because the age of the request has already become older than before the server could even see it. So there is something being missed here. The age of the request is already old. But then the request comes into the system. We make a query to the database. The database gets the query request, sends us results, and the result ultimately goes back to the server. The server generates the HTTP response, for example, and that's how the customer gets what they wanted. So when there is a request spike, and request spikes happen, Black Friday sales happen, when there is a request spike, first thing we notice is there is an increase in the number of requests which are in flight. I'll call this as work in progress, or WIP, because from the customer's point of view, we got some work which we could not do. So that's work in progress. Work in progress increases when there is a request spike, but also there's an increase in the age, because the request waited before the server could even see it. So when there's a request spike, there's an increase in the WIP and increase in the age, right? Now let's reset everything. Black Friday is over. All is good. Everything is operating optimally. Let's now say it's Friday evening, and the database becomes slow, because that's when databases become slow, Friday evening, right? So databases can become slow for a number of reasons. Let's not get into that. But if it does get slow, what happens is we see a similar kind of slowdown, but this time it's coming from downstream, from the right in this picture. And because there is a slow dependency, there is, again, an increase in the number of WIP, number of work in progress items. Again, from the customer's point of view, it is still the same. It doesn't matter if there are more requests in flight, if there were more requests made by other customers, things are not getting done. And that is something concerning. WIP increases when there is a slow dependency. Through no fault of the users this time. There is no Black Friday. Something went wrong internally. The impact is still the same. But because the database is slow, the age of the request also increases, which means that because each query is probably taking a bit longer. It takes longer time for the request to come out of the system, and then overall age of the request increases. So regardless of the cause, if there is a spike in incoming requests, Black Friday sale, or because of a slow dependency, Friday evening slowness in the database, there are two common effects. One, there is an increase in the work in progress, or WIP, and there is an increase in the age, which is how long a request stays inside the system. Now, the interesting thing about these two metrics is that they are leading indicators. Now, what are leading indicators? These are indicators that we can observe inside the server before things actually escalate, right? So going back to that Grafana dashboard, we saw that the client was already observing a latency, and that was flagged by the alert. But this was after the fact. By this time, the system has degraded so far that things have gone really bad. What we would rather do, or what we would rather want to do, is not have the client latency increase to 2 minutes ever. If this happens, this is bad. So in terms of resilience, we need to prevent this from happening. So how do we do that? Let's assume for a minute that we have this magical mechanism of measuring age and WIP. We saw that in the analytical picture sense of the term. Things can be detected by WIP and age. So let's say, by some magical mechanism, we are able to measure the age and the WIP of requests during this outage. If we look at the age, we see that there is a strong correlation with the latency. But the difference is, this is being measured by the server on the fly, before the customer is impacted. So if we could measure the age inside the server, then we could do something about it before the customer is impacted. So that's number one. Second, we also said that the WIP is an interesting metric, so let's do some magic and say that we'll observe the WIP. WIP is work in progress, and we see, again, the same thing. There is a hockey stick growth in a metric we don't want to grow. What this means is that there is too much work piling up. So if you look at the metric, I don't know if it's readable, but there are thousands of requests that are just pending in the system, and that's growing. Right? It's growing from 1,000 to 2,000 to 3,000, and that just means that there is more work coming in than the system is able to keep up. And that is congestion. And there's probably no better indication of congestion than to just look at these two graphs. The server was complaining that the server was not complaining that the processing time is constant. Each request is still taking the same amount of time as it was before, but what is increasing is the waiting time. So before, the processing is constant, 3.5 seconds, but the waiting time is in minutes. So even before the server starts processing, the request is just pending waiting. And this is very similar to a traffic jam. In a busy city, during office time, you might see this. It's pretty common. If you have for example, if you're stuck in traffic, you just can't go back, you can't go forward, you just have to wait. In the network, this is called congestion, is a sustained state of network overload, when the demands for resources exceeds the supply, right? So look at this one car. This car's driver, maybe they have a dinner reservation or something. They cannot go back home. They cannot make it to that dinner reservation. They're stuck in this car. And this is not something we want in our systems. We don't want our users to be in this car. Just detecting this is not good enough, right? We just don't want to keep our users hanging like this. We need to do something about it. So how do we make the flow of requests resilient to such things? Well, first of all, we already noted that during congestion, there's an increase in WIP, that is work in progress. That is the number of requests that are not yet completed inside the system. We also saw that the requests are getting old before they could be responded to. So the age of the request is steadily increasing. So, well, why don't we limit it? Because now we know that this can be observed on the fly by the server. So we can try to limit the WIP and the age and see what happens. So when a request comes into the system, right? Think of a doctor's chamber. A request comes in. There is usually a waiting area, like a doctor's chamber, until the doctor is ready to see you. Maybe there's a patient before the doctor, and then you will get called into the doctor's chamber, right? So even in systems, you have this implicit queue that is there where requests are waiting just before the servers can pick it up, right? Start serving the request. And because most of the time, like 99% of the time, the waiting time is negligible. Most of the time is spent in processing the request. We'll almost always see that the response time is close to the processing time until it is not, right? Until there is load accumulating in the system. And this can happen for a number of reasons. So for example, there's a spike in the requests, a Black Friday sale, for example, or a slow database on a Friday evening. But soon, when there is enough buildup of load in the system, the defining parameter in your response time is not going to be the processing time so much, because let's say the processing time is almost constant. It's the waiting time. Because look at the red request here. You have to wait for the yellows, and then the greens, and then even get a shot at getting processed, right? So your maximum time that you're spending inside the system is just waiting. And this happens when there is congestion. Said another way, the response time is dependent on the waiting time. The waiting time itself is dependent on the length of the queue, because you have to wait for all of the requests that are waiting in front of you before you. So in Albert Heijn, if you're behind someone, you have to let them check out first, and then you get it, right? Just to flip the narrative, we can say that if the queue length is long, your waiting time is going to be higher. Your response time is going to be higher. So here's a crazy idea. If queue length is causing my response time to slow down, why don't we make the queue smaller? If we make the queue smaller, that is, don't allow many things to wait, then the waiting time will be less, right? So that's how we reduce the WIP. We don't allow a lot of things to wait. But we also said that there is this age metric. When there is congestion, the age increases, which is kind of saying that requests are getting stale in the system, right? So we can filter out those stale requests. The notion here is that if it takes 2 minutes, probably the user has closed their phone by now, right? There's no point in responding to the older requests that are in the system. So clear them out in the interest of making the system more responsive. So if you implement the age filter here and have a smaller queue, there is a chance that you make a request and it's just not processed by the system because there's no space in the smaller queue, or it is just getting dropped. So you need something like a gatekeeper that says, oh, I see that there is no space in my system right now. Please try again later, gracefully telling the clients that, hey, I'm not able to handle you right now. I will take care of you if you come back a little bit later. Like in HTTP terms, that could be a 4 to 9. Similar to the dentist analogy, if you're going to the doctor's chamber, you see that the waiting room is full. A receptionist telling you that, oh, you know what, we can't accommodate you right now. Please try coming back on, I don't know, Tuesday morning. That might be a much better experience for me as a customer than to go into a crowded waiting room with no regard to when I will get to see the doctor. That is absolute disregard for customer experience, and we cannot let that happen in production. So what are we really trying to do here? We are doing 3 things. First, we are ensuring that our clients never wait longer than a certain amount of time. We do that with a smaller queue size. The queue is not infinitely growing, so the waiting time is not infinitely growing either. Second, when we know that we are not able to accommodate a request, we gracefully degrade our service, and we communicate that to our client that we won't be able to accommodate you. Please come back again later. When there's congestion, we gracefully degrade our services. And third, whenever there is congestion, there is usually a cause for it. It could be a spike in requests, it could be a downstream dependency, it could be a bug, but once the cause for this congestion is mitigated, the age filter is there to ensure quicker recovery. By disregarding the stale items of work, the work that is probably not relevant anymore, in the interest of better, more fresher requests to recover the system. So 3 things: bounded wait time, effective communication, and quicker recovery is the reason why why we would like to limit WIP and age. So how would we implement this? So I just know Java, so I'll just do that here. We started by saying that we want to limit the queue size. So in Java, yeah, when I get to Java, this gets stuck. Yeah, OK. So we started with a smaller queue size, so we can do that in Java very simply with a link blocking queue with, say, 30 slots. So if ever there is more than 30 waiting requests, we'll just say that we can't accommodate it. And that's our WIP limit, work in progress. We want to execute these requests on a thread pool that is backed by this limited queue, just like the diagram there. So we create a thread pool that uses this small queue size. And when a request comes into the system, we execute that request on this thread pool. And because we want to implement the age filter, we take a snapshot of when the request comes into the system so that when the request does get picked up, we can say that, oh, you have waited for so long, you're probably too outdated when I pick it up. So if it is too outdated, say longer than 5 seconds of waiting time, we'll just drop it. We'll not process it. But this is a request response system after all, so we have to send something back to client. So we build a response object. This is a very Spring-specific thing, but it's very similar to futures and promises, where we use a deferred result in which the response will ultimately be put in by one of the threads. So if the age filter kicks in, we say, please try again later. This request is not something I can serve right now because of congestion. But if it is not filtered out by the age filter, we respond by doing the work that was ultimately asked of us by the client. If we wrap that in a method, return the response, and map it to the HTTP endpoint, here, get hello, then that's the entire implementation. It's pretty simple if it fits in a slide, and the concept of it is also very simple, but this is something that is, the full implementation is available on my GitHub repository, and I would like to ask you to go check it out, because all the Grafana dashboards and the implementation itself is implemented in a way that you can try out with different parameters, but I won't have time to run this today. So we'll look at the results, but please do go try it out. It's just a Docker Compose file with some servers and clients, but it really highlights the importance of looking at WIP and age to make systems resilient. So we started off by saying an e-commerce website had a Black Friday sale. So let's implement that same scenario in 2 servers. One is the default implementation, which does not have any limit on WIP or age or anything like that. And then there is our other implementation on the right, in which we do have a WIP and age limit. So on the left is the default server. On the right, we have the improved server. Now, in this particular scenario, we are increasing the request rate by 2x. So from 60 requests per second, it's going up to 120, which is not a lot. It's 2x increase, but it can happen, especially in a situation like Black Friday sale, right? So let's see how these two perform. So the default server, as you saw in the beginning, is quite unresponsive. It's, in this example, it's going up to 4 minutes, which means that each request is taking 4 minutes for getting a response. That's really bad. But the improved server, if you see, there is some degradation, but the degradation is not much, especially if you compare it to the default server, which is in minutes, and this one is in seconds. So that's already a win there. But this is an incident that gets mitigated. So there is a spike that was happening. The spike eventually dies down. Black Friday is over. But even after the incident duration, the recovery time for the default server is much longer than the duration of the incident itself. So even though the cause is mitigated, there are no spikes, the system is still sluggish, the default one. The improved server recovers immediately. The moment the cause of the failure is removed, that is the spike, the system is back to normal, right? And that is a very good thing to have, because otherwise, our customers are suffering even if the cause is mitigated. In fact, the default server's latency continues to increase even after the cause is gone. So let's say you're on call, middle of the night, you see there was a spike in requests. Requests have gone down, but your latency is still increasing. What do you do now? Who do you call for help? Ghostbusters, maybe. If you look at the response statuses, right, the default server blindly responds with 200, pretending everything is fine, not knowing what is going on inside its own servers, and just spitting out 200s. So imagine if you had some kind of an alerting mechanism where you're looking at the response statuses. You see it's 200s, you're fine, you're closing your laptop, you're saying you're good, but you're really not. The improved server, on the other hand, somehow detects there is this extra load, and it responds with 429 for just that bit. For the yellow bars here, which sit on top of the green bars, green is 200, yellow is 429, it gracefully degrades, says that, OK, these are the requests I can't do right now. Please try again later. And this can also signal to your observability teams or your alerting teams that there is something going on. Please look at it, right? So that's graceful degradation. That's very helpful for the greater good of the larger system. So this is the extra work that somehow the server just knows, right? Now, let's say Black Friday is again over. We are now going to the other side of the system and say that all the other things are equal. The spike of requests has gone, but this time the database has become slow, or some dependency of your service is slow. So both of these servers, again, all input conditions are the same. Except this time, the processing time increases from 3.5 seconds to 6.5 seconds for both. Again, this time, the default server becomes unresponsive, quietly taking in work, not knowing it can't keep up, but still reducing the customer experience by going to 2.6 minutes for each request. Who would wait for that long? The default server takes 2.6 minutes. Improved server takes some seconds. Yes, it is degraded. Yes, it is not performing optimally, but at least it's not so severely degraded that you're completely stuck. Again, the incident lasts for a while. It is mitigated, so say the database latency increased for a while, but it went down eventually. But the default server, again, takes a longer time to recover, especially when compared to how long it takes for the improved server. The improved server recovers almost instantaneously. And if you look at the response statuses, the default server, again, pretends everything is OK, not knowing what is going on, not knowing the load that is building up inside it. But the improved server gracefully degrades itself. Interestingly, this time, there is no spike in requests, so the total amount of work in the system is the same. However, there is some kind of a valley that has been created now by the yellow requests. It's like we were able to do this many requests before, but due to something, our capacity to do work has reduced. And this has happened on the fly. The same implementation that you saw before, which was rejecting extra work, is now operating at a reduced capacity, and it's able to detect it without no additional knowledge. This is really powerful, so the server is able to degrade itself when it knows that it's not able to keep up. But these are two local servers that I showed you. These are local measurements that I did on my local servers. But I'm talking about microservices, and microservices don't have one machine. They have multiple machines. So does this scale globally? So when a request comes into your system, it doesn't go to this one machine. So doing these local measurements of WIP and age, I don't know, right? You will have more machines. Requests will get spread out across all of those machines. But just because you have infinite machines doesn't mean you have infinite capacity, right? With enough force, you will be able to see that let's say, with enough number of users or some dependency that is degraded, the effect of load accumulation inside the system as a whole will be noticeable in each of these servers, right? Each of these servers will be able to notice that the WIP is increasing, the age is increasing. And it's similar to, let's say, Albert Heijn or a supermarket, where you go to during rush hour, and you see there are multiple cash counters. Each of them have a queue, right? So we are doing local measurements, but the impact is globally. It's felt globally. And the reason why this works, even though we are making local measurements, is we are not really focusing on the servers individually. We are really focused on the request itself. So if there are 3 servers, but everything is working fine, there is no accumulation of load, requests are getting responded to in time, then it's fine. 3 servers are doing a great job. But if there are 300 servers, but an individual request is taking much longer than it should, then there is a problem. So by measuring the requests locally, what we are really doing is we are trying to understand if our system is able to make requests flow through the system fluidly, or are they getting stuck. And that is why when there is a spike of requests, we are able to handle it. When there is a reduced capacity in our own systems for no fault of anyone else, we are also able to handle that because both of those situations are possible. So on the one hand, it acts as a rate limiter. On the other, it acts almost like a circuit breaker. And all of this works on the fundamental principle that we are dynamically estimating capacity. So capacity is not a static thing. It depends on runtime parameters of our ability to do work. So basically what we are doing is we are trying to understand how well we are able to keep up with the demand of work. And for this request response kind of system, it is to measure whether requests are flowing through the system or getting stuck, getting accumulated. We use 2 very simple metrics, age and WIP. Age is the time a request spends before it is responded to, and WIP is the number of undone items or incomplete items in the system, both of which are locally measurable in each server, no matter how many servers you have. But they're independent of all of the system characteristics. I didn't tell you how big my machines are. I didn't tell you how many users there are. We didn't even talk about CPU, memory, GC, or even the type of requests. And that's why they're universally applicable. Because we are focusing really on how much we are able to keep up with the demand that we have to serve. In fact, it doesn't even have to be a computer system. You can have a Jira ticketing mechanism, and this method of measuring age and WIP still works, because all we are doing is we are trying to measure, are we able to meet our demands? That's it. It works for Kafka. It works for request response systems. It even works for Jira boards. And that is probably why in 2023, Google came out with this paper where they shared their YouTube's load balancer called Prequel, where they balance load not based on CPU utilization, but they use estimated latency and request in flight. And estimated latency is kind of similar to our age metric, and request in flight is similar to our WIP metric. And they use this to balance requests globally across YouTube servers. So it works for YouTube to use age and WIP in a manner of speaking. But the internet, since the 1980s, has been around. We are using it. And it also has congestion control baked inside it. So the internet uses TCP, and TCP has congestion control baked inside it. What TCP does, essentially, is that it tries to maximize the use of your bandwidth. So it keeps sending more and more network packets until it reaches a timeout, which, at least in our terminology, is detection of when an age is too high of a packet. And the moment TCP detects this on your computers today, it will reduce the WIP. And that is the number of in-flight packets. And this continues until the network utilization stabilizes. This happens in TCP today, and it is regarded as one of the reasons why TCP stood out as a successful network protocol since the 1980s. So again, in a manner of speaking, age and WIP control congestion on the internet, right? So that's what we are doing in our microservices. But let's come back, right? TCP is a big thing, but we live in a world of microservices, and not just one microservice. We have multiple. We started by saying that one microservice calls another, and something goes wrong in the middle, right? So to misquote Leslie Lamport, failure in a microservice you didn't know existed can make your own microservice unusable. And that's really a possibility today, because everything fails all the time. And this is something that I think the CTO of Amazon is famously quoted to have said. We already saw that there are bursts of traffic that can cause us to slow down. There is dependencies that can be slow, grinding us to a halt. But there are a number of other things, right? There could be latency bugs, memory leaks. There could be background processes and whatnot. So would you leave your phone unlocked in the middle of the room and go away? You wouldn't. So why would you leave your systems open to these kind of failure traps? Especially if you have a system of microservices where you depend on other microservices, which depends on other microservices. And if one of those systems has a problem, and failures can happen, and they do happen, then there is a chance that its caller gets affected, and then its caller gets affected because the downstreams are slow. And soon, before you know it, this failure cascades up to everything, and everything is red. So what started off as a local failure can become very catastrophic in the blink of an eye in this microservices world. What we are essentially trying to do is not pretending that there will be no failures. There will be failures. We are trying to limit the radius of it. And in congestion, what we are trying to do in the terms of congestion, failures due to congestion, we are trying to communicate that, yes, we know that there is congestion. We tell our clients that we are not able to handle you. Please do not expect us to respond to this work. We will get to you when we can. And then we recover quickly whenever there is a failure detection. And that fundamentally is resilience by design. What we are doing here, we are trying to build a system that doesn't just topple over with the slightest force that it gets, because it gets all kinds of force in production. What we are trying to build is a system that has a natural tendency to fall back to its stable mode of operation. And in high school physics, this was called stable equilibrium. In terms of congestion, what we did, we started with measuring what matters, and what matters is the flow of requests. What matters to that, what matters is what matters to the customer, and that is the flow of requests. End-to-end flow of requests. We used system agnostic metrics, which are locally measurable, but universally applicable. Fundamentally, to recognize that sometimes we will just not be able to keep up with the demand. What happens in that situation, how we react to that inability, how we detect that we are not going to be able to meet the demand, is resilience by design. And that is how you control congestion in microservices. Thank you. I'm happy to take any questions.
Thank you, Mourjo, for your talk.
If there are any questions, I'm happy to take them.
She's coming.
Yeah.
Yeah, thank you for the great talk. And I guess that identifying a systems constraint with this method is quite useful, but then subordinating it, so I guess you kind of use something like that to instruct something like KEDA or a similar scaling solution would also do something, even if you have stabilized the queue. The question for me would be, you'd probably want to implement some kind of logic in your front end or your service to prevent a thundering herd problem later down the road, right?
Yeah, that's a good question, but sometimes some problems are just not solvable, right? You might get attacked. Some requests are just not what you want to serve. But it is possible to not just limit requests. As you said, you can say that, OK, we know that there is congestion in the system. That means that we don't have enough resources, fundamentally. Sometimes it is possible to add resources to it, right? If our servers have some latency bug or something, adding more compute will solve it, but not always. For example, simplest case that I can think of is if you have a central database, adding more services is not going to help. Right? You'll have to rethink your model. So not all problems of congestion is solvable, but at least detecting it is one step closer to not letting everything else fail. That's the starting point, I would say.
Thank you so much.
Thank you.
Thank you. Any other questions?
Did you have a question?
Yeah, I was going to ask something like that. Yeah. Spin up in parallel or container or something like that.
Yeah. Yeah, spinning up is just going to increase your compute, but you're limited by the amount of things that you have all together, right? So yeah, database is a good example, but sometimes you just can't do more. And just scaling up is going to make the problem someone else's problem. So if you scale up your HTTP servers, it's the problem of the database. They'll have to think about what to do, so yeah.
Okay, thanks. There is another question over there.
Given that you are able to measure the, let's say, for 2 nines and then the number, the graceful degradation, can you share maybe an example where you can use it as a lagging metric as well for some kind of root cause analysis, or is it valuable also as well?
Yeah, as a lagging indicator, you usually have this out of the box. So you usually would see that the client is getting a slow response, right? So anytime the customer complains, you will see it in the caller services side that some downstream dependency is very slow. In root cause analysis, the equation is a bit different because the things have already happened in the past. So you can drill down into which service was slow and for what. Usually, it would also help to notice the number of requests and the latency that you are observing from each of those services. And I would probably use something like a distributed view of your queries and your requests as they flow through the system. So for lagging indicator or a post facto, let's say, analysis of the system, I'd use slightly different metrics. But I guess you could use the same. This one, the ones I showed, is more for reactive than for later on analysis. The traditional metrics like latency, number of requests, statuses would usually help you to understand what happened in the past in the system. But as things happen, that is much harder, and this usually helps there. But I wouldn't use this for root cause analysis. That would be going back to the different services, how they were called, and how many requests there were, and checking the end-to-end view, I guess.
OK, makes sense. Thanks.
Thank you.
Yeah. One more? Yeah.
Yeah, thank you. Just continuing the question from there, like for the retrospective analysis or the root cause analysis, is there any idea that it passes from service to service so that you can identify when was the breaking point or to follow it?
Yeah, I would go for something like distributed tracing. You know, there's these tools that pass on the same kind of header that maps one request and tries to look at how much time you spent on one service. Similar to flame graphs, I guess, on the system. You can have that. I think there are tools as well available which does this, where you can see the entire path of a request and see how long you spent in each service. So that would be really helpful in understanding why something went wrong at a certain time.
Thank you. Thanks a lot. We have time for one more question over there.
Thank you for the nice talk. I would like to know about the downsizing the queue, which we are considering as a WIP. So how can we find the most affordable and the accommodating queue size which can be fit in our system? Do you have any metrics or anything, or it's all about just trial and error?
Well, in short, it depends. But yeah, that's a very good question because it depends on service to service. This queue size really depends on how much you can afford to let wait, for example. So in some services which are very, very latency sensitive, you maybe want a very short queue size because queue is just the elasticity of the system, which means that how much you're affording to extend the lifetime of a request if immediately it is not servable. So it really depends on your service. But as I said, 30 is a very good metric. But on the other side, sometimes you just don't want it to wait at all. In that sense, you might want it to reduce even further, depending on your use case. How much can you afford to wait for it to eventually get successful? So on the one side, you have giving the customer an experience that you're not able to serve them. How often do you want this? On the other, the risk that if you take on more work, you're going to cause some kind of an outage. So you have to draw the line between these two when you decide the queue size. So it really depends on system to system.
Yeah, I think WIP and the age, which is both are very closely related, and it's a bit tricky to find the sweet spot in between.
Yeah, age is very easy to understand because age is a time metric. So if you have some kind of a, let's say, a connection timeout or a response timeout on the client side when the request comes into your system, that's your age metric. So you never want any service to take, say, longer than 30 seconds. 30 seconds is a very high number. So you can put that as a top-level high limit. That can be your age, for example. Whereas the queue is the one that you really want to play around with. So age is more like you're allowing the system to recover quickly. That's not so much as configuring the system. Your configuration is mostly on the queue size. How many things do you want to take on in terms of when congestion does happen? Do you want to give those a shot, or do you want to just give up? So age is the higher metric. I would say that put it at a connection level parameter that you never want your customers to wait longer than 30 seconds, and then configure the queue.
Makes sense. Thank you.
Thanks a lot. I guess there is one more question to go.
Hello, my name is Kase, and I wanted to know if those principles are applied the same way to asynchronous and synchronous communications systems.
In principle, yes. Not so much as the way I described it. In asynchronous communication, the implementation I showed you is basically converting a synchronous call to an asynchronous call by using a thread pool of sorts. But if you have an asynchronous container, like a reactive system, there is some way you'll have to contain the amount of work you take on. So it won't be as direct as I showed it, but the amount of work you do is the same in terms of whether it is synchronous or asynchronous. So sometimes you just can't keep up with the incoming requests. And if it is asynchronous, you'll have to do probably a little bit more to configure the system than what I showed you. But it's still your capacity to do the work is limited by how much resources you have and how much work is coming in.
Thanks. Thanks a lot for all the questions. Thanks, Mourjo, for the deep dive talk. Another applause for him, please.
Thank you.